Okay, now we're going to start jumping into phase diagrams. Now we had one of these last time with the liquid, or the water and sugar phase diagram. But now we're going to add something a little bit different. Because for most cases, we're going to have many different phases, and we're also going to have more than just a solid solution and a mixture. There's going to be things in between. So if we look right here, this is the copper nickel system. And right at the bottom, we see the weight percent nickel. So as we go to the right, this is 100% nickel. If we go to the left, this is 100% copper over here. There's only just two components. There's only two independent variables. That's temperature, our y-axis, and concentration, which is the x-axis. And you can also change the pressure, and that does change things, but 1 atmosphere is what's almost always used because most things are under 1 atmosphere of pressure. And there are two different phases. There's the liquid, there's the solid, and then there is a mixture in between. But the mixture is in a different phase, it's just when I have multiple phases at the same time. There's also 3 different phase fields. So this is 1, 2, and 3 right there. So I have the liquid, the solid, and a mixture. And so it shows that depending on my concentration and depending on the temperature, I'm going to have different points. So as I mix these two together, I'm going to reach this point of a mixture earlier as I get rid of nickel, and I'll reach it later as I add more nickel. So this system is a binary system. It's binary because there's only two components. That's copper and nickel. It's also called isomorphous because there's complete solubility of one component in another. And that means that that alpha phase field, where I have this nice solid solution, it extends from 0 to 100% weight percent nickel. You don't see that with everything. With iron, you go to I think it's 3%. That's the max you'll see, because beyond that point, the steel just breaks down and eventually you turn into pencil lead. And so obviously pencil lead and steel do not mix. So how do we look at these phase diagrams? Well, there's various rules we're going to use to help us look at it. First off, rule number 1. If we know the temperature and our concentration, then we know which phases are present. So, for example, if I know I'm at 1100 degrees Celsius and 60 weight percent nickel, there's one phase, because I am right here, and that is a single phase. We're not in the mixture area. However, if I'm at 1250 degrees Celsius and 35 weight percent nickel, there are two phases, both the liquid and the alpha, because I'm in that mixture region in between. For rule number 2, if we know the temperature and the concentration, then we can determine the composition of each phase. Now this is not as easy. We're going to get a new tool a little bit later to help us with this. I'm going to show you the method to do it right now. Because one thing you might be wondering is, this is 100% liquid. That's 100% solid. What about this one? Is this 60% liquid and 40% solid? How much? So here's how we do it. First off, we're going to consider this point right here, which is 35 weight percent nickel. And we're going to start at 1320 degrees Celsius. And currently at that point, it's 100% liquid. The concentration of liquid is the same as my concentration. Okay. And if I go down to 1190 degrees Celsius, then the concentration of solid is the same as my concentration. So it's going to be 35 weight percent nickel. But what about right here in the middle? Both the solid and the liquid are present. And we're going to create something called a tie line. So this tie line simply says, this is my center, and this goes straight over to whatever my first phase line I'm going to cross is. That one goes straight over the other one into whatever phase line I cross. And so that's going to help me say, okay, this is a mixture of liquid and solid. And depending on which one you're closer towards, you have more of that there. So if I'm closer to the liquid side, I have more liquid. If I'm closer to the solid side, I have more solid. So if I look right here, I see that the concentration at the liquid side is 32. And the concentration at the solid side is 43. So the concentration of my liquid is equal to this point right here where I'm touching the liquidus line. The concentration of my solid is right there, and the liquid is going to be 32 weight percent nickel, and the solid is going to be 43 weight percent nickel there. Okay. So now that we know that, we can now determine the weight fraction of each phase. Remember before, this was just saying the composition of each phase. So I was able to tell fairly quickly that just by looking right here, I can see that my liquid is going to be 32 weight percent nickel, and my solid is going to be 43 weight percent nickel. So they're different. But now I want to see what the weight percent of each phase is, because this is overall 35 weight percent nickel. So at my temperature A right up here, only liquid is present, and so for my weight fraction, the liquid is 100% and my solid is 0%. Down at the bottom, it's only solid, so that's 100%, and my liquid is 0%. But then I have this point right here in the middle where I have both liquid and solid. And so how do I figure that out? Well, I'm using that tie line. And so you see that I've made a little variable here. So S is for the distance to the solid, R is for the distance to the liquid. And using that, I can figure out the weight fraction. So like I said earlier, the one that you're closer to is the one you have more of. And so I'm closer to the liquid line. And you see in the end, I have 0.73. That's my weight fraction for the liquid, and only 0.27 for the solid. And to figure this out, it's simply for the liquid, you say, okay, what is the distance to the solid? I know that seems very strange, but there's a reason for it. What is the distance to the solid over my total distance? And for the solid, what is my distance to the liquid over the total distance? Okay, so hopefully this setup makes sense. I know this equation right here, it seems backwards, but as we see next time, you're going to make a lot more sense about why it seems backwards, as we introduce what's called the lever rule. So thank you for listening, and I'll see you all next time. Have a great day. Bye-bye.